Continuing the solutions to test number 2, we are now on number 6, the first real problem of the test. So number 6 says a 75.0 kilogram suitcase on the ground is being pulled to the right by a horizontal force of 450 newtons. The suitcase does not have wheels, and the coefficient of static friction is 0.650. Sorry, I forgot to, it didn't copy over. While the coefficient of kinetic friction is 0.585. So we're asked to decide if the suitcase moves. And then we're asked in part B, what is the magnitude of the friction force? Okay. So here's a picture of the situation. It's a very simple situation. We're just on horizontal ground and we're pulling an object with a given force. But we also have friction. Now, when we get into the details of friction, friction is not a conservative force, so we're probably not going to be using the energy approach. We're also not going to be using the momentum approach because we don't have time, or we're not asked about the average force or anything like that. All the forces here are constant. I should point that out. So that just makes it a straight up F equals ma kind of problem. And whether or not the suitcase moves, we know that the way we approach this is we assume it doesn't move and see what the static frictional force would be, and then we compare that to what we can figure out the maximum static frictional force can be and see if it all is okay. If it exceeds the maximum, then it is moving. So let's assume it's not moving. So the free body diagram situation is we've got the force going this way, and we've got, of course, static friction would oppose the way it would move, and if this was frictionless, it would of course move to the right. And so if this thing is not moving, then it has zero acceleration. So F equals ma. We'll have a 0 in for A. So we have that the sum of the forces is 0. Now the sum of the forces is our pulling force is positive minus frictional force going the other way. That has to equal 0, which of course means that big F and little fs have to balance. They have to equal each other. So little fs equals F, which we know is 450 newtons. So if you're pulling with 450 newtons but it's not moving, then static friction must be balancing that with 450 newtons in the other direction. Now, that's if this thing is to stay still, that has to be the case. So now the question is, can static friction be that big? So the maximum static friction is, and we use our convenience formula of mu s mg. In other words, mu s times the weight of the object. And we're allowed to use this convenience formula when we're just on a horizontal surface and the only vertical forces are gravity downward and normal force upward. Then this is what it comes out to be. So we can just jump to that. All right, if you put the numbers in, and that works out to be 478 newtons. So the maximum that static friction can be in this case is 478 newtons. We only need it to be 450 newtons, so that's fine. So the answer is it does not move. The maximum static friction has not been exceeded. If it had, it would start moving, and then we would switch to kinetic friction. Okay. Now, question B, what is the magnitude of the friction force then? Well, as we said, it's 450 newtons. We've already done the work. Just to be clear, it's not the maximum. The maximum is just how far it could have gone up to, but it didn't get up that high. It just needed to balance the 450 newton force to the right, so it's 450 newtons. And that's the answer. That's all it is. If static frictional force were 478 newtons, to the left, it would be actually more than F, and the object would start accelerating to the left, and we know that's not what happens. Okay. Number 7. A 1,530 kilogram car is put through a crash test. It is driven into a wall. It approaches the wall at 15.0 meters per second, and after the collision it rebounds off the wall in the opposite direction at 2.60 meters per second. The collision lasts 0.150 seconds. The question is, what is the average magnitude of the force exerted by the wall on the car? So in this problem, the first thing you have to decide is, like, what's your approach? What kind of problem is this? Seeing the word collision in this problem might make you think to use the elastic or inelastic collision approaches, ideas that we did in chapter 8. But here's the problem with that. We only really have one object. We don't have two objects that are colliding. And when we did those collisions in chapter 8, it was two objects running into each other. We used conservation of momentum because there were no other forces. And the whole point was to predict the final velocities. So we knew the velocities as they came in before they hit each other, and we wanted to know like which direction and how fast they were moving after they hit each other. But this is, again, I know the word collision was used here, but this is a completely different situation. There aren't two moving things or two things that can move. There's only one thing that can move. Now you might say, well, the wall is the second thing. But the wall can never move, and the wall is attached to the building, and so the building would be exerting forces on the wall, so it wouldn't be an isolated situation. It wouldn't be an isolated system. So we can't treat it like one of those two-object collisions and try to use conservation of momentum. It just would not be appropriate here. The other thing is we have time information, and that never came up in those collision problems. All right, the fact that we have time also rules out energy. If you remember, the energy approach really does not involve time at all. It doesn't use time. It doesn't tell you time. Time is not an issue. Time just doesn't play into the energy approach. So that leaves the momentum approach, and that's exactly right for this. The momentum approach very much uses time. Right, impulse is a force over a time. And that approach has a very definite equation that gives you the average magnitude of force. So that's really, this is tailor-made for that kind of a problem. So in other words, we have an initial velocity of 15.0 meters per second to the right, let's say to the right. And a final velocity, now this is one of those things where you have to remember to switch the signs because it's going in the opposite direction. So negative 2.60 meters per second. Right. So we have an initial and a final momentum where you multiply by the mass. So we put in the numbers for the initial, and we get 22,950 kilogram meters per second, or Newton seconds, right, was the alternate unit. And then for the final, negative 3,978 kilogram meters per second, or Newton seconds. And so the formula that we want to use is that the change in momentum is the average force times the time that elapses. Or the average force is the change in momentum divided by the change in time. So we can figure out the change in momentum, and we have the amount of time that elapsed. And so we plug everything in. The change in momentum, so the final minus the initial, so this negative number minus this positive number, negative 26,928 Newton seconds divided by the 0.150 seconds, giving us newtons, right? And the number is 1.80 times 10 to the 5th newtons. Negative, but if we just want magnitude, then we'll just make it positive and call it 1.80 times 10 to the 5th newtons. Of course, it's to the left because that's the way the wall is going to exert its force on the car. And that's the answer. But I think, again, the main thing was realizing what kind of a problem it was. And so you don't want to forget, and we had done this early in this, in the material for this test. We did the momentum stuff earlier. It was right after the last test. And so it was easy to sort of forget about that, but that's a really important tool to answer a question just like this. Okay, we'll stop this part of the video and we'll start a new video to continue.